Hello everyone, this is Quincy from University of Utah. I'm going to present our work in applying machine learning for EDA, specifically leveraging LSTMs and transfer learning for exploring design flows for synthesis. This is a work done with collaboration with Dr. Wang Zhou from IBM TG Watson. We recently saw many works on applying machine learning techniques in EDA domains. The main motivation is, although EDA is still an automation tool, but now it requires a lot more manual efforts for tuning the design flow to get a good performance. The main reason comes from the increasing complexity of the design and technology, but moreover, the big challenge comes from the large design space, slow evaluation, and the lack of predictability of existing EDA tools. Machine learning techniques are believed and have been used to improve the predictability in many applications, so is also believed to improve the predictability of the EDA tools, which can be used to accelerate the design space exploration process. So let's see an actual design exploration example from industry, which was the first task of my internship at IBM. So my manager asked me to test where should I use these sequential options, in this case is retiming, inside a regional flow. So we were expecting that at a certain position of the flow, applying these sequential optimization options will provide improvements in terms of QR, such as delay and power. At the beginning, the task looks very trivial to me. So let's assume that we have 200 steps. So we can plug in the flows like this. Or we can use another option, right? So then you can quickly get an idea how many tries you need. In this specific case, assume you have 200 flows at the beginning and you're going to have about 40K options. So I was thinking 40K isn't a really big number, so I just need to write a script and let it run. And then I start saying the problems. So the design we worked on are split into 7 pieces, and evaluating each of these sub-design takes about 20 hours. So it takes about almost a week to evaluate the entire design with one design point. Okay, so if you do a little bit math, then you realize for a year you can only evaluate 52 out of 40K, which is obviously not reasonable to accomplish this task as an intern, right? So, but I was really happy to see these real-world problems, which becomes a strong motivation to me to do research in applying machine learning for CAD. So let's discuss and summarize the limitations and the challenges of traditional EDA flows. The main reasons why exploration of EDA flows is extremely challenging are mainly caused by the large design space, and due to the increasing complexity of the EDA tool flows and the technologies, such design space is increasing constantly. More importantly, at most of the stages in the design flow, the tools are actually giving us some estimations of final QR performance. Unfortunately, due to a large number of abstraction layers we are using in synthesis and physical design, those estimations sometimes are way off the actual QR, so can be very misleading in design exploration process. Moreover, when we are having new technologies and new design comes in, due to the limited domain knowledge of these new things, exploration becomes even harder. So recently we have seen many works that leverage machine learning techniques to improve and accelerate the design exploration process, especially in synthesis. There are two main trends in this direction. The first one is based on training a machine learning model with static dataset that are very well engineered with feature extraction strategy, such that the model can be used to focus on unseen synthesis flows or options without actually running the design flows for a given design, which can be very consuming. It is basically used as a more fine-grained and accurate focused options or functions compared to the original estimators built in the design flows. The other direction is applying reinforcement learning strategy into the design exploration process. The nice thing about reinforcement learning is that it does not require static dataset at the beginning, and the model can be adapted to different technologies and designs without any further engineering of the model. Unfortunately, due to the extremely time-consuming process of each design flow iteration, it is impossible for a large design, such as the examples we just reviewed. Similarly, limitations are valid for the first option as well, because preparing a large amount of dataset can be very time consuming due to the same reasons. So in this work, the general idea is to leverage machine learning techniques into design flow exploration process, such that exploration can be guided by a more accurate and fast estimation model, so we can print out a large number of design space without actually testing them. Our main objective is to address the limitations that we discussed in previous slides. First, we aim to develop a machine learning based system that will significantly reduce the number of training data for adapting the model from one design to another or from one technology node to another. This will significantly reduce the computation efforts in both data collection and training process. Specifically, we propose to leverage transfer learning, which is a technique that will enable reusing the knowledge learned from the previous training process for a different but similar machine learning task. In order to do that, we need to improve the robustness of the model to achieve high accuracy in terms of transfer learning. This is because we aim to restrict the number of data points for transfer learning or retraining process to be less than 100 data points. This is very aggressive. So we propose a novel feature modeling and develop a simple LSTM-based recurrent neural networks to forecast the QR, which is modeled as a regression task over the previous state-of-the-art that is formulated as multi-class classification problem. So let's quickly look at what type of synthesis flows we're targeting in this work and how large the design space can be. First of all, we use open source framework ABC to demonstrate the flow and our results. Specifically, the flows are targeted are basically the same as sequential decision making problem. As shown in these slides, we collected a few basically 3 synthesis transformations from ABC as refactoring, rewriting, and balance. So if you don't know ABC system, it doesn't really matter. Just keep this in mind. Each of these transformation is one decision you can make. And while developing such flows, you can always change the position of the transformations, and also you can repeat the transformations multiple times. For example, here we assume we have 3 different transformations, and each of these are repeated twice. So we call this a 2 repetition flow. This is basically a permutation problem. Each of these decision paths shown in this figure is one synthesis flow. Notice that each of these paths applied to a given design will result in a different QR, most likely, which is exactly what we want to forecast using machine learning models. This design space of this type of M repetition flow is shown here. As you can see, the design space can grow extremely fast if you increase the size of n, which is the number of transformations, and m is the number of appearance of each transformation. So in more complex flow settings, such that each of these transformations might repeat different times, so we also provide a more generic formula to calculate the space of the flow, where you can see m1, m2 correspond to the number of appearance of each different transformation. Now we understand how the flows are developed, we also understand how the space look like. We would like to give you some idea about how crucial the exploration process can be. We generate 50K random flows with random permutation, and then we apply all of those into a 128-bit AES design. First of all, we can see that different design flows have a very different QR performance. In this case, we have observed about 20% difference in terms of delay and 40% difference in terms of area. Moreover, we can see that during the random sampling process, most of the design points are actually located in the bad performance area in this case. Because among these 50K random data points, we can see there are a large number of points are located on the top right, which is the worst in terms of delay and worst in terms of area. So your next question will be, how does these flows do compared to the default design flows in ABC? Well, we run 3 of those. It's called resyn, resyn 2, and resyn 3. We actually apply those 4 times. Okay, so unfortunately, all of these handcrafted design flows in ABC are still performing pretty bad. They are all located in the worst QR distribution region. One of the main targets of this work I have mentioned many times is enabling cross-design exploration. Here is an example why this is very important and why it is very challenging. We applied the 50K random flows to two different designs. First of all, we can see the distributions of these two designs are very different, although they are using exactly the same 50K random flows. And more importantly, we take two of the best performing flows for the arithmetic unit and we applied it to the AES to see how it performs. And then it turns out these 2 points are performing pretty bad for a different design, which is the AES. So in summary, the design flows have to be carefully developed for different circuit structure. Unfortunately, between different circuit structure, it is very hard to forecast using the same model. Let's get into the details of our proposed approach. As mentioned earlier, any flow includes a set of transformations that perform iteratively. We illustrate the concept of timed model of synthesis flows, which are used as the feature representation to our model training and inference. Specifically, we pick the default ABC flow Racing, which has 6 different transformations to illustrate this model. The timeline of applying Racing to this design is shown in this figure, where you can see each transformation in the flow is actually applied to the design at a certain time frame. For example, from the time range 0 to T1, the transformation basically balance is applied to the design. And then the second transformation jumps in starting at T1 and finish up at T2. So the whole flow will finish at T6. So for each transformation at a certain time step, we can use very simple one-hot encoding to encode each of the transformation at each time step. For example, here we can use 100 since we only have 3 different transformations to represent B and 010 to represent rewriting. So we can see that model actually naturally represent the sequential decision process of sequential synthesis flows. So which can be also extended to a more complex timed model. So where you can actually extend the encoding based on the real runtime of each transformation. For example, rewriting could be more complex than balance. So let's see, assume it takes twice more runtime compared to balance, and then you can simply extend rewrite to a 3x2 dimension vector that indicate it actually takes twice longer than balance. So a more complex example can be shown in the same fashion. In this case, the timed model represents a 4 repetition flow with 6 different transformations. That's why you can see this is a 24 in terms of length. Notice that each of the decision paths, this is flashing here, will have a unique representation using this modeling. So one of the challenges for machine learning for CAD is data collection process. In general, getting labeled data points for machine learning for CAD tasks are very challenging and sometimes could be impossible. Notice that we are talking about labeled data points. This problem has been discussed also in many other machine learning for CAD stages, such as physical design. The previous state of the art for flow exploration introduces a customized multi-class labeling strategy, which generate labeled data points based on domain knowledge and unlabeled dataset. So such that this dataset can be used to train a classifier to recognize good flows or bad flows. However, since the labels are customized and the labeling rules are defined by the users, this could decrease the quality of the dataset. For example, we tested 2 different labeling rules where we only change the labeling rules for the best QR flow classes, which is class 0. And the model performance is changed dramatically. Notice we only interest in the top flows, which is class 0, and the accuracy of estimating class 0 is the most important one. So unfortunately, we can see that the second labeling rule is V off, is only 46% in terms of accuracy, but the first one have 98% accuracy. So However, there's no way to evaluate these labeling rules before you actually have trained the model and tested. So it's almost impossible to define which one or decide which one labeling rules you really want to use. So instead, in this work, with more natural modeling we just discussed and carefully developed neural networks, we're going to discuss that in the next slides. We can switch to a regression model to directly predict QR metrics such as delay and area to eliminate this issue. Here is the architecture that we used in this work. It is an LSTM-based recurrent neural network that is trained to do regression tasks. It includes 2 LSTM layers and 3 fully connected layers. We also included batch normalization and dropout to improve the robustness and prevent overfitting. The details of our training setups can be found in the paper. To evaluate our approach in a really comprehensive way, we have prepared a large number of datasets. Specifically, we have collected over 400K data points with 12 different designs and 3 different technologies, because we are going to evaluate how transfer learning and how our approach will perform cross technology and cross design. The dataset have ground truth labels in area and delay, and the flow size is 24 time step long. So as mentioned earlier, one of the key techniques we used to reduce the number of required data points for adapting the model from one to another is transfer learning. So as shown in this figure, our target is to reuse the model that is trained based on 40 nanometer technology dataset such that the model can be applied to a new technology, for example, 7 nanometer dataset with less than 100 data points for retraining or transfer learning. So the main intention is that we believe, although the QR distribution can be different between different technology libraries, there are still common knowledge or behaviors shared between the flows and QR matrix. Specifically, we have implemented and tested 2 different transfer learning strategies on our proposed model. The first one will only use the new data to update the fully connected layers. So where we can start the retraining process with initial weights trained from 40 nanometer dataset. Okay, so that is shown in the first green arrow here. Similarly, for the second approach, we also started from the pre-trained weights using 40 nanometer dataset, but we updated the entire trainable parameters of our model, which is the second arrow shown here. And our result shows that the second approach is better than the first one, but both give us a much better results, and we are going to see that in the next few slides. The first set of results here demonstrate how our approach performs in terms of cross-technology estimation. In this case, we pick Galois field multiplier dataset collected on 40 nanometer for initial training, and we use 100 data points on 7 nanometer technologies to do transfer learning. Notice that this is still within the same design, but different technologies. So first, we can see that within the same technology, the training and testing are all on 40 nanometer, which is the first figure, and it fits extremely well along with y equal to x line. But we are more interested in how it performs cross technologies, right? So the bottom 2 figures shows cross technology prediction results with only 100 data points used for retraining or transfer learning. We can see that there's some degradation in terms of prediction performance, but both cases are fitted also very well along with y equal to x line with only 0.5% mean absolute percentage error. So we also tested for cross-design estimations using the proposed approaches. First of all, we can see that our approach outperformed the state-of-the-art with highly restricted number of retraining data points. Specifically, we tested retraining with 150 and 25 data points. A second observation is that result between the 2 different transfer learning strategies we implemented. And we observed that updating the entire model using transfer learning outperforms the other. However, we do see that cross-design transfer learning is much more challenging than cross-technology because design structures can be so much different. This is something we are definitely interested in investigating more in the future. Thank you.